Well, that was certainly good for me. Hopefully that was a great session for you. Really helped to coalesce a lot of what went on today, which I know personally my mind is swimming. Just amazing. I think obviously one of the key points to reaffirm is just get involved. It's early days, and it's an industry that's only going to grow exponentially as the years come. So now we'd like to work towards wrapping today with our keynote toward fault tolerance, and we'll see if we can get Pooya on with us on video, and then I'll hand over the floor.
Do you hear me?
We can hear you. Welcome.
Perfect.
Thank you. Thanks for joining. So pretty much my role here then will be to hand you the floor, and thank you very much for helping to close this out today, and I'll come back on at the end of your presentation.
Absolutely. Yeah, thanks so much for the invitation and for the opportunity to talk a little bit about what my group at qBraid is working on. So I titled the talk as Towards Fault Tolerance, but I added a little more detail here so I plan to talk about hardware software co-development, with an eye towards fault-tolerant quantum computation. Before moving forward, my name is Pooya. Happy to be here. I'm director of the Hardware Innovation Lab at qBraid. I've been with qBraid since its inception. It's about 8 years, I guess, that I worked with qBraid. Through that time, I've worked on applications, working with different groups inside qBraid, forming different kind of research groups and R&D groups. And some of those researchers that were trained by me or did research and collaborated with me graduated into other parts of the organization, working on different parts in closer to applications, closer to quantum devices, near-term quantum devices. And Hardware Innovation Lab is a little bit newer than the other parts of the organization. It's about 2 years that we are active with the vision that I hope to be able to explain in the next few minutes to you. So one of the things that we worked on in those years was really looking at computational challenges of industries in different sectors, in energy and finance, healthcare, manufacturing, operations management, and all of these industries and different processes in each of these industries come with lots of computational challenges that require different types of exotic and accelerated hardware to improve the processes that exist in the industries today. And so we've been working in qBraid as an organization on bridging the gap between these industry problems and the hardware that exists, either conventional hardware, CPUs and cloud computing resources, machine learning accelerators, GPUs, FPGAs and things like that, and also quantum inspired and quantum devices that have been coming through the past decade online, and we've been trying to see their applicability to different industry problems. So one of the things that this kind of taught me, and I do come from a computer science background, but I speak the language of the physicists well enough to be able to be a bridge between physicists and computer scientists, was that it really showed me as a person who was usually working more on the theoretical side, but now was working more on the applied side of things, how impressive and effective the classical computational tools we have are in solving industry problems. And that observation led to us obtaining kind of a realistic picture between what is required by industry and what is the status quo in quantum computation. And this is not at all an objection to the status quo in quantum computation. I think it's very impressive where we are and how we've got to this point, but it's important to also be realistic about the scale of the computational challenges that industry is facing, and manage that difference. And because of that, this led to over the years me being able to devise kind of an application first R&D program to bridge the gap between industry and quantum computation. So some of the lessons that I've learned through the years from working on quantum algorithms, devising quantum algorithms, analyzing different quantum algorithms, is that designing practical quantum computers and quantum algorithms to run on them is a long-term effort, and we have to think about it that way. So some of those lessons include the fact that quantum algorithms, if you have worked with them or if you've read some introductory quantum algorithms textbooks, you will notice that there are certain type of building blocks that repeat themselves. So for example, quantum Fourier transform, or quantum phase estimation, or quantum amplitude amplification, quantum circuits for executing classical arithmetic on floating point representations or fixed point representations. All of them, all of the quantum algorithms we kind of think about and build, especially when we are talking about quantum algorithms that process classical data, they get broken down into sort of building blocks that I call them core computational tasks for a quantum computer. And those core computational tasks do come with a lot of structure in them. So they have certain patterns. The circuits are, we don't write the entire circuit when we are talking about the quantum algorithm. We write them in terms of kind of modules, and then we understand what goes into those modules. But then if you zoom in into one of those modules, you will see a lot of other, a lot of repetitive patterns that show up, a lot of structure that shows up in those other circuits, and you can keep going like that. So this is the way, when we think about quantum algorithms and designing quantum algorithms, we work on it. We don't really draw the entire circuit, but we understand what goes into each of those modules. Okay, so I think it's important that the second lesson for me is that it's important to understand that we have to exploit that structure when we are thinking about building hardware software stacks for quantum computing, and how we would integrate these building blocks when we're thinking about applicable quantum algorithms. The third lesson for me was that quantum algorithms are resource savvy. So they take a lot of quantum resources. Here I've shown you a table of solving very small satisfiability problems. These are not industry problems, but they have features of industry problems. And you will, if you look at the counts of the number of gates, like CNOT controlled gate, controlled NOT gates, different types of Hadamard, T gates, and so on, you will see that they grow very fast to, very, very soon you get to tens of millions of qubits for sizes that are not too large. I mean, these probably these last rows are not something you would run on your laptop comfortably, but it's certainly easy to still do an exhaustive search on them. Whereas for a quantum algorithm, you would need to be able to run millions or tens of millions of gates. And so that's, that tells us that we need to get to be able to run hundreds of millions of gates or more than that. Like, this might be an optimistic, even lower bound for industry applicable quantum circuits, but we certainly want to work towards getting to hardware software stacks that can run these types of circuits. So being able to provide resource estimations, which is the number of qubits, the number of gates, the types of measurements you would have to do on them, being able to do that allows us to say, okay, so how robust should our quantum circuits be? How high the fidelities of each of the operations that our quantum computer is performing has to be, and that provides actual targets, like application driven targets for fidelities of and qualities of the gates and the qubits in our architectures. And so all of that goes into helping us develop and optimize the integration between the quantum processors and the classical coprocessors that have to provide that robustness into execution of our quantum subroutines, or those core computational tasks. Okay, so this led to us founding the Hardware Innovation Lab at 1qBit. And in the Hardware Innovation Lab, I started working more closely with the physicists. So we have expertise in physics and computational aspects of the full stack. This includes people who have background in experimental aspects. They've worked in superconducting labs and trapped ion labs and other quantum technologies. And they have the background in optimization and machine learning computational aspects so that we can have the right type of skill sets to provide that collaborative environment. And so that is being used to develop the software ecosystem required for different parts of the stack when we collaborate with our hardware partners. So this includes writing compilers, transpilers, schedulers when we are breaking down the quantum program that is written by the quantum programmer down to a simpler or lower level language for the quantum devices, how we would perform error correction, what type of error correcting codes we have to use, what type of fault tolerance schemes we would deploy, and how would the decoders work as the quantum chip is performing quantum operations. So all of that lets us, it's kind of an R&D work that we do with our hardware partners, but the side product of each of those R&D projects is the fact that it advises us what are the software ecosystems we have to provide to this fully co-developed kind of hardware software stack. So that includes the compilers, includes the software packages for characterization, calibration of the devices, and software packages for quantum control and realizing the quantum gates that the experimentalists are interested in developing. So all of these are different fields in a way in quantum information processing. Like you probably know experts in each of these areas. Some people are experts in characterization and validation. Some people are experts in quantum control. Some folks are specifically focused on error mitigation or error correction techniques. And then we have like people who are more closer to the applications or like computational aspects of the field, working on quantum algorithms, classical quantum hybrid algorithms, applications, and architectures. But what we have been trying to do is basically bring these kind of siloed efforts together into one group. So we have our hardware collaborators on one hand, and then our hardware innovation lab is composed of groups that have expertise in all of these areas. But the difference is that when we work on these areas, we are each of those groups is informing requirements and targets from the other group involved. Okay, so I already talked about applications. So I have the luxury of being able to talk to lots of people in qBraid that work on healthcare applications, that work on pharmaceutical, that work on banking, financial, computational finance applications. And we see the work that happens in like, what is the state of the art methods that these groups are developing, and how would quantum computing be able to help move the needle in the computational requirements that these application kind of partners in qBraid have. And that leads to the years of research we have done in quantum algorithm design. I'm just showing you some of the archive preprints. I wouldn't go into the details, but feel free to contact me or look up our people and their archive links to read some of these exciting work. Some of these algorithms are related to how you would use quantum computing to accelerate or change the way we solve problems that today we solve with machine learning. Some of them are related to optimization problems, operations research, different type of processes that industry needs to optimize, and some of them are related to quantum simulation techniques and applications in quantum material, quantum chemistry, and so on. Okay, so how does this help us build better architecture? So you probably have seen von Neumann and know him as a genius mathematician and physicist. But one of the things that amazes me about von Neumann is that he was also a very, very great engineer. So there's this, it's a fainted cover of a paper, a report that was called First Draft of a report on the EDVAC. So qBraid was one of those early kind of, this is the picture of qBraid, which was installed in a building at the time. This report was generated in 1945. And by the way, this report got really famous in those days of development of classical computers as the first draft. And so this was an important report. It was kind of an unfinished report. Von Neumann didn't really finish writing it up in a way that would have been published. But certainly it's available. I think you can look up the original text of it. And so that's the first place that von Neumann talked about classical logic, for example, arithmetic on fixed point numbers or arithmetic on float point numbers. At that time, they were trying to just be able to add and subtract and multiply fixed point numbers, very small precision. So the observation that was exactly what I was saying, that these circuits have a lot of structure. And if you were to just compile that arithmetic circuit into machine language and try to get the cycles of kind of your main processor to perform them, then you will have to spend a lot of cycles of your machine on just performing arithmetic. So this was the first place that in the history of kind of classical computing that von Neumann suggested arithmetic should happen somewhere else. And those cycles that are used for compiling or executing the rest of your assembly instructions should happen in a different processor. And so that's the way I think we should think about those core computation tasks that I was talking about, and think about designing architectures for each of those core computations separately and having them integrate with each other when performing a larger quantum circuit. So for example, in a quantum computer, you would have to think about how many data qubits you're going to use, how are you going to entangle them, how are you going to perform those harder gates that are more prone to errors. These are called non-Clifford gates, if you're familiar with the term. And these non-Clifford gates will, they take their own really large amounts of resources to generate them. So we talk about things like magic state distillation, and there's a magic state factory that performs magic state distillation and provides a distilled magic state somewhere in a port that would be able to get entangled with the data qubits. So how would this architecture, like if we are thinking about a 2D architecture, how does this have to look? What are the geometries that will optimize performing different circuits? They will look very different for quantum amplitude amplification versus quantum phase estimation. And that's what we do in architecture study and optimization. So the architectures are important then to apply them to be used in the compilers and how the jobs are scheduled. But then at the heart of the architecture is the physical layer. Those little dots that I'm showing in these pictures are the actual qubits in the device. And we would have to think about what are the types of error correction protocols we're going to use? What are the cycles of error correction that has to happen? What are the classical coprocessors that are called, for example, decoders have to do? And how fast does each of these operations have to happen? All of these would change our kind of engineering decisions when it comes to writing compilers, schedulers, and the architecture for the device itself. Okay, so there are other techniques that, sometimes quantum error correction itself is expensive. And maybe is not the right tool for different applications. For example, if you're talking about analog quantum simulation, then there are other procedures that are often called quantum error mitigation techniques that have to be used. Quantum error mitigation is likely important as a classical post-processing step, even if you have a fault-tolerant quantum simulation of a system that you're interested in. And so I refer you to this preprint from our group that shows a machine learning technique for performing error mitigation, which we call neural error mitigation. And so quantum neural error mitigation is used in this demonstration on IBM's devices. It's a very small chip. I think it had 5 or 6 qubits. We were able to perform a simulation of a small molecule here called lithium hydride, and neural error mitigation was used to mitigate the errors in that simulation. So down lower in the stack is the work that we do with our quantum hardware partners on building the gates with the qualities that are needed for those applications that are informed in the top of the stack. So this is kind of a very, very interesting innovation cycle that our team goes through. It starts from using optimization and machine learning techniques to build gates. Then we perform experiments with our experimental partners on those gates, and we see if we are realizing what we thought we are devising in numerical simulations. And so we have to validate those experiments and then try to extract more information about the system. What are the dominant sources of noise? How would we inform the quantum control expert to mitigate those errors or to overcome the challenges that we found in the experiment, but we weren't seeing in numerical simulations? And this cycle keeps going until we get to the target fidelities of the gates and qubits that we have to achieve for those applications that we have in mind. So the nice thing about working in quantum control is that it's closely related to other areas in computer science, including optimal control, machine learning methods for optimal control, such as reinforcement learning. And so you would see, if you look at this paper from Carl Mills that was working on his PhD thesis with me as an intern in 1QBit, and we use reinforcement learning not in the low level, in the level of controlling quantum gates, but we use techniques that we were developing to study quantum gates and develop and control them better to, in fact, navigate how a larger quantum simulation at the algorithm level would go. And we can see that these techniques can actually improve the conventional methods that are used for example, Monte Carlo simulation of many-body systems. Okay, and then last but not least comes the hardware partners that we collaborate with. We have multiple hardware partners in different technologies. I wouldn't bore you with going into every one of those technologies, but a couple of them that I can name here is Seek, that develops hybrid quantum classical platform with us to minimize error correction overheads needed to support advanced applications in quantum chemistry and machine learning. And another partner we work with is the work that we do with NTT Research in quantum optics and and quantum photonics. And the primary goal, again, there is to devise stacks for algorithms that are applicable in machine learning and optimization with these other types of quantum technologies. And with that, I'll be happy to take any questions.
Thank you, Pooya. If you have any questions, you can submit them in the Q&A. Just really an amazing way to wrap up and kind of cover everything we've covered today, from the educational aspects to the physical aspects to the coding aspects, all of it. Thanks for helping us wrap this up. Hang some compliments on
It was definitely a pandemic period, but I kept it.
We appreciate it.
How does quantum relate to machine learning? Yeah, there are different directions. So one direction is to think about how would you use quantum computers to do a better job, either in machine learning or in tasks that today we use machine learning to solve. So you might have heard of terms like quantum machine learning, and people mean different things by quantum machine learning. Sometimes they're talking about just using quantum computers to take the same protocols we use, kind of those data-driven protocols in machine learning, in classical machine learning, and then achieve quantum advantage for them. Other ways in which machine learning, and then the other direction is that machine learning can itself be used, and we use it like the same way machine learning is everywhere in your devices and image recognition, natural language processing, all the applications that are deployed in edge computing that we use every day, they come from machine learning techniques, and they can also be used to think about how would you optimize your compiler, how would you build architectures, design better architectures, and then how would you control the quantum system and tackle the errors that it is prone to. So all of those are areas that classical machine learning can help build better quantum devices.
Knowing that this is the kind of end of day keynote, maybe you can leave us with kind of your thoughts on where the industry is headed, or what you're most excited about going into the year ahead.
Yeah, well, I think I think that obviously the first milestone was quantum supremacy, and we know that there was a lot of years of impressive work that has gone into achieving quantum supremacy. But quantum supremacy is in this context, we're using it in a technical language, which is find a task. Don't worry about whether it's useful or it's an industry relevant task. Find a task where we can all, as a community of computer scientists, physicists, mathematicians, agree that classical computers would not be able to tackle that task, and show that with a quantum computer, you can tackle that task in really, really short amount of time, like in minutes. And I think the next obvious milestone is, so can we change that task to make it useful? And there are different directions to go. You can start from things that look like quantum supremacy experiments and try to look at those algorithms and see if you can find applications for those algorithms. The other way is to look at what textbook quantum algorithms are and try to build devices that can run those textbook quantum algorithms. The problem with the second approach is that it takes a lot of time, and you might be in the dark working in the labs and on your computer for years and years without having a checkpoint to make sure that your development is in the right direction. So the other way is to kind of meet them in the middle. So you work both on making smaller, lighter quantum algorithms that are applicable, or they're a demonstration of what, if you scaled it up, would be applicable with a convincing kind of a computational argument, and then build quantum devices that can execute those smaller but useful quantum algorithms. So that's certainly the direction we are taking. And to be able to do that, like I was showing, even for very, very small quantum algorithms, you would have to build, you would have to be able to execute millions of gates, which is not something we can do on the devices that exist today. So you have to think about, not only the way we have studied error correction and fault tolerance, but also innovate new methods for error correction and fault tolerance that would allow you to build devices, scalable devices that can unlock those demonstrations.
Well, I think that's a perfect place to end. Thank you very much for
No problem.
for keynoting for us and joining us. Yeah, like I said, we'll move into kind of just some closing thoughts from our end at BRIC, but incredibly appreciative of the audience that joined us today. Can't say enough about the fact that everyone that presented, especially Pooya still on the line with me, having representation from 40 countries and 170 different metropolises is we're truly grateful for that. So, as well as like to thank our partner in this, which would be qBraid. Don't forget to sign up for qBraid on their site, use their platform, or just use it as a place to get updates and information on some of the things going on in the world of quantum, as well as our joint events. We'll be announcing soon some future events around this, as well as getting into more details about those micro grants and where that program might be headed. I'd like to thank the team here at BRIC. So we have an amazing production team behind the scenes of Chris, Caitlin, and Jason, who have made this all possible today, as well as our friends over at the Center of Rural Innovation. Molly Pyle specifically was very integral in helping us to recruit some of today's presenters. And once again, we thank you. We hope you have a wonderful weekend and really look forward to exploring this amazing industry as these new milestones get achieved. So have a great day, everyone. We appreciate it.